Introduction to concavity. Let's begin by informally defining concavity. A function is concave up on an interval if it is opening upward on that interval. So the way I like to think about concave up is that that portion of the graph can hold water. So in other words, it's sort of the shape of a bowl that if I were to pour water in it, the water would actually stay in that bowl. So on the left side of this graph here, I have a concave up interval. So from -1 to 1 on this graph can hold water. It is considered to be concave up, opening upward. And on the other hand, a function is concave down on an interval if it is opening downward on that interval. So in other words, that portion of the graph cannot hold water. So on the right side of this graph, so from 1 to a little past 3 here, I have a graph that's opening downward. It cannot hold water. It looks like an upside down bowl. So this portion of the graph is considered concave down. So that's a general informal way of thinking about concavity on the graph of f of x. So this would be the original function f of x. Now take a look at the definition of a point of inflection. We say that c, f of c, is an inflection point of f of x if the concavity changes at x equals c. And c must be in the domain of f. So this blue point here has been labeled as our inflection point because I had a change from concave up to concave down. But I could also have a change from concave down to concave up. Now the inflection point must be written as a coordinate point. So the inflection point is some xy, or c f of c, as stated in this definition. Now recall that when we talk about critical points, even though it has the word point, it's sort of poorly labeled because we really only write down the x value of the critical point. But in a point of inflection or inflection point, we actually have to provide both the x and y value. So we want it to look like c f of c. Let's move on now to explore the formal definition of concavity. So we need f of x to be a differentiable function on an open interval from a to b. Then f of x is concave up on the open interval from a to b if f prime of x is increasing on the open interval from a to b. So let's stop and think about what this means. F prime of x is the derivative. So a function is concave up if the derivative is increasing. So let's go back to how we should think about derivatives automatically is we should reference slope of the tangent line. So what this is saying is that a function is concave up if the slopes of tangent lines are increasing. So let's go ahead and take a look at the image below. So we've looked at what it means to be concave up formally. So this portion of the graph informally is an upward facing bowl. But now let's see if it matches our formal definition. So we want to make sure that the slopes of tangent lines are increasing. And these three red lines here are three different tangent lines on the portion of the graph that we recognize to be concave up. And let's analyze from left to right what's happening to these slopes of tangent lines. So this first slope is a negative slope. And this middle slope here is meant to look like a horizontal line, which has slope 0. And then as I move to the right, this line has positive slope. So remember, we read graphs from left to right. So on this interval, I have a slope that goes from negative to 0 to positive. So that collection of slopes is increasing. So that means on this portion of the graph, my function is formally concave up. As opposed to concave down, a function is concave down on an interval if f prime of x is decreasing on a to b. So the exact opposite, slopes of tangent lines must be decreasing. So the slopes must be getting smaller. So we'll reference the blue portion of the graph that we recognize to be a downward facing bowl, and we'll look at the slopes on this concave down portion of the graph. So on the far left, I have a slope that starts out positive, and then I have a horizontal tangent line, and then I have a slope that's negative. So from left to right, my slope was positive, then 0, then negative, so the slopes are getting smaller. So formally, this portion of the graph is concave down. Alright, in this first example, let the following be the graph of f of x. Identify the inflection points and the intervals of concave up and concave down of f of x. So this is the graph of f of x, the original function, and we want to find where this graph is concave up, concave down, and then find the inflection point. So I'm going to go ahead, and before I write out the x intervals where concavity occurs, I'm going to go ahead and color in each of those intervals first. So I'm going to start on the far left side of this graph. So as I start to draw this graph, I can see that it looks like a downward facing bowl. So this portion of the graph is concave down. And so this boldened point here is to indicate that there is a change in concavity that occurs at this x value that we're calling a here. So in blue, I'm going to choose to represent all intervals that are concave down. So this first interval is concave down, and then as I move along, I have all upward facing bowls. So I'm going to skip over to this x value at C and start to draw what looks like another downward facing bowl. So another interval of concave down. And then at D, it looks like I changed to a concave up interval. So if I were to write my intervals of concave down, since this graph is going left forever, I'm going to start at negative infinity and go all the way up to the x value a. So I'm concave down from negative infinity to a, and I'm concave down from c to d. So these would be x values on the x-axis. We're just generically representing them as variables. So my function is concave down from negative infinity to a and from c to d. And just like intervals of increasing and decreasing, they're defined to be open intervals always, so we don't have to consider the endpoints. Now I'm going to highlight my graph wherever it looks concave up. So I look like a concave up or upward facing bowl on this region here and on this region here. So on the intervals from A to B and B to C. And I also look concave up past the x value D. So if I were to write those in interval notation, I have concave up from A to B and concave up from B to C, and then finally concave up from D all the way to the right, so all the way to positive infinity. So these are my intervals of concave up and concave down. So now I want to find the inflection points. So I had a change in concavity from concave down to concave up at A. So because we don't actually have the y values here, I am going to express my inflection point as a f of a. Even though I don't know the exact y value, it still has to be written as a coordinate point. Alright, so now there is no change at b, so I am a concave up function and I stay a concave up function past b. So now c is kind of a tricky one. So I do change from concave up to concave down at this x value c. But there was a part of the definition of a point of inflection that said that c needs to be in the domain. So there is no actual function value at c. There's this vertical asymptote, so the graph is growing up here, and there's a hole in the graph down here at this left open circle. So I have this point of discontinuity, and that means that if c is not in the domain, it can't be an inflection point. So I would not include c. But I would include D. I do have a filled-in circle, and I have a change from concave down to concave up at D. So D, f of D, would be the second inflection point. So C is not an inflection point because the function is not defined at C, so it's not in the C is not in the domain, so it cannot be an inflection point. All right, let's move on to an important theorem regarding concavity. So let f of x be a differentiable function on an open interval from a to b. Then the original function f of x is concave up on the interval from a to b if the second derivative is positive for all x in a to b. And the original function is concave down on a to b if the second derivative is negative for all x in a to b. So this theorem is important because it relates concavity to the second derivative function. And previously our formal definition used the first derivative function to define concavity. Well, now if we want to find intervals of concave up and concave down, we can find where the second derivative is positive to find intervals of concave up, and where the second derivative is negative to find intervals of concave down. Now, we also want to know how to find inflection points. So this next part tells us how to test for an inflection point. We want to assume that the second derivative exists for all x in the interval from a to b, and we want c to be a point in AB. So if that number c is an inflection point, then either the second derivative at c is 0, or the second derivative at c does not exist. So we need the second derivative to be 0 or not exist to be an inflection point, but more than that. And we also need the second derivative to change signs at x equals c. So if the second derivative changes sign, then the original function changes from concave up to concave down, or concave down to concave up. And remember, an inflection point is a place where concavity changes. So not only do we need where the second derivative is 0 or doesn't exist, we also need to show that concavity changes at that point c. And then f of x has a point of inflection at c. So there's one additional step past finding critical points, where critical points we just need to set the first derivative equal to 0 or find where the first derivative doesn't exist. Inflection points is one step more, where the second derivative is 0 or doesn't exist, and we need the second derivative to actually change signs at c. We need a change in concavity to be called an inflection point. Alright, so now let's go over a methodical way of finding inflection points and intervals of concavity of f of x. So to find inflection points, the first thing we're going to do is find all x values where the second derivative is 0 or undefined. Now, these are possible inflection points. We don't know their actual inflection points until we can decide that concavity really changes at those values. The next thing we want to do is plot the possible inflection points on a number line to break it up into x intervals. So this is similar to what we've done in the past for intervals of monotonicity. We're then going to pick a test point from each interval to substitute into the second derivative. Now we're doing that to find the concavity of each interval based on the result of the test point. So if we take that test point and decide that the second derivative is positive on that interval, well then f is concave up on that interval. And if the second derivative is negative on that interval based on the test point result, then f is concave down on the interval. Now if concavity changes between consecutive intervals from a to c and c to b, then the coordinate point cf of c is an inflection point. Alright, first example, find the points of inflection of 3x to the fifth minus 5x to the fourth plus 1, and determine the intervals where f of x is concave up and concave down. So to find possible inflection points, we're going to need the second derivative. So we have to find the first derivative. By the power rule, we get 15x to the fourth minus 20x cubed. Now we need the second derivative. So we're going to get 60x cubed minus 60x squared. And we're going to need to set the second derivative equal to 0. So I'm going to factor out a 60x squared, and I'll be left with x minus 1. So I would set each of these parts by the zero product property equal to 0. So I would set 60x squared equal to 0 and x minus 1 equal to 0. So I would get x equals 0 and x equals 1 as my possible inflection points. That's how I'm going to label these. So now what I need to do is break up the number line into intervals. So my number line is going to go from negative infinity to my first possible inflection point 0 to 1 to infinity. And so I need to break this up into my potential intervals of concave up and concave down. So negative infinity to 0, 0 to 1, and 1 to infinity. And then I need to choose my test point. So my test point in this first interval, I'm going to choose negative 1. Between 0 and 1, I'm going to choose a half. And 1 and infinity, I'll choose 2. And now what's important here is what we substitute the test points into. So this number line is all about the second derivative of f. So what we want to do is find the sine of f double prime of x, because we want to know about concavity. And if the second derivative is positive, we have concave up intervals on f, and if the second derivative is negative, we have concave down intervals on f. So we're substituting these test points into the second derivative. Now I'm going to choose to substitute them into this factored form. And remember, I only care about the sign, positive or negative. So if I plug in -1 into this x, well, that will always be positive because it's being squared. But -1 minus 1 is -2, so multiply together, I'm going to get a negative. If I substitute in a half, 1/2 squared is always positive. 1/2 minus 1 is going to give me another negative. And if I substitute in 2, so the quantity on the left is always positive, 2 minus 1 is positive, so I have positive. So now let's think about whether f is concave up or concave down on each of these corresponding intervals. So since the second derivative is negative, f is going to be concave down. We have another negative second derivative, so this interval is concave down. And this final interval is positive second derivative, so we have concave up. So determine the intervals where f is concave up and concave down. So f is concave up from 1 to infinity because f double prime of x is greater than 0 on 1 to infinity. We have f is concave down on the interval from -infinity to 0 and 0 to 1. Should have been a u there. Because f double prime of x is less than 0 on each of those intervals, -infinity to 0 and 0 to 1. So that's the conclusion about the intervals of concave up and concave down. But now inflection points. So it turns out that even though 0 and 1 were possible inflection points, we can eliminate 0 as an actual inflection point because concavity does not change at 0. So right here at 0, we stayed concave down over those two consecutive intervals. But at 1, we changed from concave down to concave up. So my inflection point is 1, f of 1. But I can actually find f of 1 by plugging 1 into this original function. So I want to do that, so I'm going to get 1. If I plug in a 1 here, I'll get 3 minus 5 plus 1. So I'll get -2 plus 1, so I'll get -1. So my inflection point is 1, -1. In this next example, I have the same set of instructions. Find the points of inflection of x to the 5/3 and determine the intervals where the function is concave up and concave down. So we're going to follow the same steps. We're going to have to find the first and second derivative. So the first derivative is 5/3 x to the 2/3. And the second derivative is going to be 10/9 x to the -1/3, or 10 over 9x to the 1/3. So I need to decide where the second derivative is 0 or does not exist. Well, the top can never be 0, so there are no zeros to the second derivative, but the bottom can be 0 when x equals 0. So my possible inflection point is x equals 0. So my number line is only going to be broken at 0, so my intervals will be -infinity to 0 and 0 to infinity. My test points will be -1 and 1. And again, I'm interested in the sign of the second derivative, so that can tell me whether f is concave up or concave down. Alright, so I'm going to have to plug -1 into the second derivative here. So if I go ahead and substitute in a -1, the bottom of this function is 1 over 9. This is the cube root of -1. So the cube root of a negative is a negative, so that means the second derivative is negative. And if I substitute in 1 to the second derivative, I'm going to go ahead and get a positive value. So I have a change in f from concave down to concave up. So I can summarize my results and say that f is concave up on the interval from 0 to infinity, because the second derivative is greater than 0 on the interval from 0 to infinity, and f is concave down on the interval from negative infinity to 0, because the second derivative is less than 0 on negative infinity to 0. So that's the conclusion about the intervals of concave up and concave down. And then it turns out that my possible inflection point x equals 0 is an actual inflection point because I had a change in concavity from concave down to concave up at the x value 0. So my inflection point is 0, f of 0. So if I substitute 0 into the original equation, I'm going to get 0. So my inflection point is 0, 0. Alright, now let's try to find intervals of concavity and inflection points given f prime of x, or specifically the graph of f prime of x. So here are some things we want to remember. If f prime of x is increasing, f is concave up. So by the definition of concave up, f prime is increasing. If f prime is decreasing, then f of x is concave down. And so that means inflection points occur on the graph of f prime of x at local extrema. So at changes from increasing to decreasing or decreasing to increasing. So let's take a look at these examples. We're given the graph below of f prime of x. We want to find inflection points and intervals of concavity for each. So the graphs do go on forever, and what I've marked here are specifically the local maxes and local mins. So we're going to look at this left graph first, and what we're going to do is find intervals where f is concave up. So what we're interested in is where f prime is increasing. So remember, this is the graph of f prime of x. So looking at this graph is increasing on an interval from negative infinity to negative 2. So from negative infinity to negative 2, this is an increasing function. So it's like I'm walking up a hill. And from the x value 0 all the way to infinity, because this graph goes to the right forever, this graph is increasing. So f is concave up from negative infinity to negative 2 and from 0 to infinity, because f prime is increasing on those intervals. So now let's find where f is concave down. So f is concave down where f prime is decreasing. So f prime is decreasing from negative 2 to 0, so where I'm walking down a hill. So f is concave down from negative 2 to 0 because f prime is decreasing on negative 2 to 0. So now that we've found intervals of concave up and concave down, let's try to look at inflection points, or find inflection points. So for inflection points to occur, we need a change in concavity. We need a change from concave up to concave down, or concave down to concave up. So we said that the original function f is concave up from negative infinity to negative 2, and then switches to concave down from negative 2 to 0. So that must mean that I have an inflection point. So I have an inflection point at negative 2, f of negative 2. So there's an inflection point at the x value negative 2, but I can't find the y value, f of negative 2, because this is the graph of f prime of x, and I don't know what f of x is. And I also have an inflection point at 0, f of 0, because f prime changes from decreasing to increasing, which means f changes from concave down to concave up. So I have my other inflection point at 0, f of 0. So now let's go ahead and try to answer the same questions using this right graph, still of f prime of x. So if this is my derivative function, then f is concave up wherever this derivative graph is increasing. So it's like I'm walking up a hill, or I'm increasing anywhere past the x value 1. So f is concave up from 1 to infinity because f prime is increasing on 1 to infinity. So that must mean that f prime, or I'm sorry, f is concave down from negative infinity up until an x value of 1, so from negative infinity to 1, because f prime is decreasing on negative infinity to 1. So there was a change from concave down to concave up that occurred at the x value 1, meaning my inflection point is at 1 f of 1. So a lot of people want to say the inflection point is at 1, negative 1. But remember, this is the graph of f prime of x. F of 1 is not the same as f prime of 1. So I would just have to write it generically as 1 f of 1. Alright, so finally we're going to find intervals of concavity and inflection points given the graph of f double prime of x. So what we want to remember is that if the second derivative is positive or above the x-axis, f is concave up. If the second derivative is negative or below the x-axis, f of x is concave down. So that means inflection points are going to occur on the second derivative at x-intercepts, where the graph changes from above to below or below to above the x-axis. So in this example, we're given the graph of the second derivative of x, and we want to find inflection points and intervals of concavity. Alright, so let's start with finding where f, the original function, is concave up. So since this is a graph of the second derivative, I want to know where the second derivative is positive or above the x-axis to find intervals of concave up. So this graph is above the x-axis from negative infinity to 0 and from 2 to infinity. So up here, so f is concave up from negative infinity to 0 and 2 to infinity, because f double prime is greater than 0 on these intervals. And f is concave down on the interval from 0 to 2, where the second derivative is below the x-axis, or negative. So on the interval from 0 to 2, because f double prime is less than 0 on 0 to 2. So to find inflection points, we want to find the x-intercepts of the graph, so 0 and 2, but more than that, we want to make sure that the graph at those points changes from above the graph to above the x-axis to below the x-axis, or below to above. And each one has that satisfying it. So at 0, the graph changes from above to below, and at 2, the graph changes from below to above as we look from left to right. So the inflection points are 0, f of 0, and 2, f of 2. And again, we can't find the specific function values, the specific y values, because this is the graph of the second derivative at x.